Hello students, so in today's class we are going to learn this topic, that is electric flux through a cylinder. Okay, so basically this is a figure, that is cylinder, a closed surface I have kept. Okay, and this cylinder will be placed in a uniform electric field. Okay, and what is the total flux coming out from this surface, from all the surfaces of the cylinder, we are going to find out. Okay, so for that reason, first we need to draw a cylinder. So this is my cylinder. You can see a dotted line from the center of that cylinder, that is the axis of the cylinder. Let's consider the electric field is passing along that axis of the cylinder. So let me mark over here that this is my electric field. The direction of the electric field is something like this. Okay, so this is the electric field. Okay, on this side also I'll mark, this is my electric field which is passing along the axis of the cylinder. To make it easier, let's mark the different surfaces. So obviously cylinder has one curved surface and on the two sides it has a circular surface, correct? So let's mark this surface as surface 1, okay, first circular surface, this surface as surface 2, the second circular surface. Let's call the curved surface as surface 3. So now our intention is to find out the total flux coming out from the first surface, total flux coming out from the second surface, and a total flux coming out from the third surface. So let's say phi 1, phi 2 and phi 3 and add them together to get the total flux coming out from the entire cylinder. So this is the thing we are going to do here. Okay, so the total flux phi is going to be phi 1 plus phi 2 plus phi 3, wherein phi 1 is the flux coming out from surface 1, phi 2 is the flux coming out from surface 2, and phi 3 is the flux coming out from surface 3. Okay, so let's start from the surface 1. So if you see, the direction of the electric field is such that it is entering the closed surface. And I had made a statement while teaching you electric flux, is that when the electric field is entering any closed surface, the flux from that surface is always going to be negative. How it is going to be negative? So explanation will be, the electric field is going this way, but your area vector always point perpendicular to the surface outwards, right? So basically your area vector is going to be this way. So let's call this area as S1. Okay, so S1 with the arrow. This is going to be your area vector, correct? So theta over here is going to be obviously 180 degrees. Okay, and what is the flux? So basically let's find out phi 1. So phi 1 is going to be E dot S1, correct, which is going to be E S1 cos of theta, and theta, if you see here, is 180. So E S1 cos of 180 degrees. So it's going to be minus E S1, because cos of 180 is minus 1. Okay, now let us go to the second surface here. Okay, since electric field is going outwards, obviously the flux is going to be positive over here. So the area vector, how do we mark? The area vector is perpendicular to the surface outwards. So it's going to be, let's say, S2. Okay, so theta in this case, if you see, is 0 degrees because they are parallel to each other, right? So let's find out phi 2. So again, E dot S2, which is E S2 cos of theta, which is E S2 cos of 0 degrees, which will be E S2, correct? And now coming to the third surface, that is the circular surface, correct, or the curved surface. So in this case, again, the area vector is going to be perpendicular. So at any point, right, at any point, the area vector is going to be perpendicular to the surface outwards. So let's say S3, sorry, not delta, S3. Okay, and the electric field, so let's consider this as a point, and the electric field is going this way, parallel to the axis, right? So what is the angle between the area vector and the electric field at every single point on the curved surface area? It's going to be 90 degrees. So theta is going to be 90 degrees here. So phi 3 is going to be E dot S3, which is E S3 cos of theta, which is E S3 cos of 90, and cos of 90 is 0. So the total flux phi from here, from this formula here, is going to be phi 1, that is minus E S1, plus phi 2, that is plus E S2, plus phi 3, that is 0. Okay, now if you see here, since it is a cylinder, both the sides, the circular area is going to be same, that is S1 is going to be equal to S2. because both are same circles, right, of same radius, right? So it's going to be ES1 plus ES1. I can very well replace this S2 with S1, which is again going to be 0. So what you can say for the total electric flux through a cylinder which is placed in a uniform electric field, the electric flux coming out of the cylinder which is placed in a uniform electric field is 0. Okay, this is going to be your final statement. So this is it for today's class. I'll see you in the next class with few more application of the Gauss's theorem, okay, to calculate the electric field at different points.